Discuss the Poisson distribution. The Poisson distribution is very simple. There are only two things you have to worry about. One is the mean, and the other is the random variable that you're interested in. We're going to deal only with IID random variables, that is, identically independently distributed random variables. Examples are accidents in a week, or customers walking in a store in a given hour, or poker hand ace king appearing X number of times in an hour. So all of these are identically distributed random variables. And the formula for Poisson distribution is also pretty straightforward, which you should memorize. Here's the formula for you. Here we go. So lambda is the mean, and x is the random variable that you're interested in. To make sense of this, let's do some examples, perhaps. So let's say that on average you get ace king 6 times an hour. You know this because you maybe checked out how many times you're getting ace king in 10 hours. Or actually, in this case, you can know this by probability itself. So we know that the chance of getting pocket aces, for example, is 1 in 221. So we know that or any pocket pair. We know that a casino deals 30 hands per hour. So on average, we will get 30 over 221 pocket aces per hour. So this becomes lambda. Now let's say we want to know the chance that we will be able to get 3 pocket aces in the upcoming hour. So we know that these are random IID variables, and so we can apply the Poisson distribution formula. So this becomes the probability that x equals 3 is equal to 30 over 221 to the power of 3 e to the power of minus 30 over 221 let's see, what did I do wrong here? Stick the minus there, and let's put all of this in parentheses and put 3 factorial here. Okay, so this is now something we can simplify on the calculator. Let's just simplify it a little bit here. So here we got a calculator, and let's do 3 factorial we know is 6. 30 over 221 is 0.135. So let's just take this guy and replace it with 0.1357, 0.1357 minus 0.1357, 6. Okay, and so let's jump back to our calculator here and do 0.1357 3. So that's 0.0025. So let's put 0.0025. And then let's get the value for E to the power of minus, what did I do wrong here? Let's clear this again. Let's do point. And how do I do a 0.1357 minus 0.1 e to the x is 0.8731. 0.8731. Sorry, I don't know how to use a calculator well, but here we go. So let's clear this again. 0.0025 times 0.8731, and let's divide that by 6. And so there we have it. 0.3 zeros and 36. So equals 0.3 zeros and 36. So that's equal to maybe 0.036%. So the chance that you'll get a pocket ace, exactly three pocket aces in the next 1 hour is 0.036%. So this is one thing we could do. We could also compute this. Let's say we wanted to know what's the chance that we will get x equals to at least 3 pocket aces. So that means we get 3, 4, 5 all the way to infinity. An easier way to do it is to do 1 minus the probability of 0, 1, and 2. So x is at most 2. Right? So that way you can do 1 minus the probability of x equals 2 minus probability of x equals 1 minus the probability that x equals 0. So you can do all of these using the same formula. And I am going to cheat a little bit, and basically I'm going to do a Poisson distribution using the 30/221 in Excel. So let's do a new workbook here. Alright, so our probability, our mean was 30/221. And we can apply the formula, but Excel makes it very easy for us because they give us the Poisson distribution formula pre-recorded in it. We just need to put in our x mean and then true or false for cumulative. We will just do x equals to 0, mean is equal to 0.1357. Okay, and oops. And let's do, forget cumulative, so let's do false. Alright, so the chance that we get 0 pocket aces is this. Let's extend this. Let's replace this one by 1. By 1. And this one by 2. And let's sum these up. And subtract from 1. So here we have it, the chance of us getting at least 3 pocket aces in 1 hour is equal to about 0.038%. So going back here, this one is equal to 0.038%. Now, as you can see, this makes sense because it's a little bit higher than the probability that we'll get at least 3, but the chance of getting 4, 5, 6, so many pocket aces is very, very low. And so they only add up to another 0.002%. So, okay, so this is one example of using the Poisson distribution. Let's say that we want to now do another example. Let's say that in any given week in a neighborhood, on average, 5 accidents happen. So what that means is basically we get, let's see if we can find lambda here. There we are. So what means lambda is 5 accidents per week in neighborhood. And then we want to know what's the chance that exactly 2 accidents will happen in this week. So if we want to know the chance of 2 accidents, we're going to write the equation. The probability x equals 2 is equal to lambda to x times e to the negative lambda over x factorial. 2 factorial is just 2. I missed it. Alright. Let's see if we can punch this into the calculator. So we get 5 squared is 25. Let's first get e to the minus 5 here. So let's say minus 5. E to the minus 5 is this. Times 25 divided by 2 is 0.084. Okay, so equals 0.084. Yep, which is about 8.4%. So if a neighborhood has an average of 5 accidents a week, the chance that 2 accidents will happen in this given week is about 8.4. So since this only relies on the mean, it's easy to plot the distributions for different Ks. And if you plot them, it looks kind of like this. Here you can see if the mean is 4, it looks like this. We did an example with mean is 5 for 2 accidents. So that was 8%. Here we can see if the mean is 4, the 2 accidents is a little over 10%. And one interesting thing to note is this initial plateau is there for m equals 1 when the mean is 1. If the mean is more than 1, we're going to get this front tail here. And if the mean is less than 1, we're not going to get the front tail. We're just going to start and keep dropping the percentages as we go to a higher x for our random variable. So in this way, you should be able to figure out for any independently distributed identical variable the chance of a certain number or a certain value for that random variable given the mean. So that's it. That's the Poisson distribution. It's very useful for real life problems. I just showed you how you can figure out the chance of pocket aces or the accidents, or you could use it for figuring out how many customers you expect on a given day or given hour. So it can be useful for modeling revenues and other such things. It can be useful for figuring out how many whales you're expecting in the ocean in a given area, or oranges in the season, any random variable. So that's the Poisson distribution. It's very simple. I highly recommend that you memorize this equation, lambda to the x, e to the minus lambda over x factorial, and lambda is the mean and x is your random variable. This is Aditya Mittal from Acmetutor, teaching Poisson distribution.